Hello, everybody. Welcome back. Another exciting episode of analysis. This time we're going to be talking about set theory. Now, I've used the word theory here, so a brief comment is definitely in order. Scientists will use the word theory to mean our current best guess, right? So we'll talk about quantum field theory or the theory of gravity or whatever. Mathematicians use theory to mean something else. When they say theory, they mean a bunch of theorems. Okay, what's a theorem? Well, we'll say more about that in a second. But essentially, it means a collection of mathematical results, a bunch of things that we know are true. So it's not a guess, it's a collection of true things that we know. It's a completely different use of the same word, which can make things a little confusing. So we're going to be talking about set theory in this video. It's not going to be, I said, our best guess at how sets work. What we're talking about is a bunch of facts that are true that we can prove using all the logic rules we studied before about sets and how they work. Now, I use the word theorem. Let me go back and put into a larger perspective what a theorem is. And so, when I was little and learning all of this stuff, no one ever explained this to me. And so, I think it's useful at the beginning to also point out what these various mathematical words mean that mathematicians throw around all the time. For example, there's definitions. So definitions are the seeds from which all the rest of everything grow. And I've said several times in previous videos, you have to have definitions and theorems memorized. What I mean is you have to know the definitions. Otherwise, you don't know where to start or what to do when you're trying to write a proof. If you're trying to write a proof about a continuous function, you have to know the definition of a continuous function so that you know what it is you're trying to prove. Besides definitions, right, from those we can start to create things that we know are true using these rules of logic. So sometimes we might call those things facts. Sometimes we might call them propositions. A lot of times those are what we will use for easy things that are really quick and obvious and only take a couple lines to prove. We'll call something a lemma if it's like a baby theorem, right? So usually a lemma is something like, oh, look at this is kind of cool. It doesn't take that long to prove and it's not terribly important. And especially we'll call it a lemma if it's something that we're going to use to prove something more important later. Okay? A theorem, okay, that's a important result that's useful and worth calling a theorem in its own right. So theorems are kind of the big things, right? Like you can imagine these are like your third and fourth place hitters on your baseball team, right? These are the big guys with the bat that comes in and is supposed to hit home runs. Corollaries are just little results that follow from a more important theorem. So you can again imagine that these are the guys batting at the bottom of the order, right? So you have theorems do the heavy lifting, and once you understand a theorem, there may be something else that's obviously true, and we will call things like those corollaries. Okay, so we've talked about the theory part of the title, set theory. Now it's time to talk about sets. So a set is a collection of objects. The objects in the sets are all elements or members. A lot of times, if I'm being slightly informal, and I am actually being somewhat informal here too with this definition, I'll say a set's a bunch of stuff. And if we try to be more formal than that, you can quickly run into situations where things get really, really messy really, really fast. So we're going to go with what's called naive set theory, meaning we're just going to say a set's a bunch of stuff. Okay? For example, if I put curly brackets, that's usually what I'll use to list the members of a set. So curly bracket 1, comma 2, comma 3 means I've got a set with the elements 1, 2, and 3. I might write something like A equals the set with the curly brackets of all integers. So those would be numbers like 1, 2, 3, 4, 5, 6. Also negative numbers like negative 3, 0, negative 15, and so forth. B would be even integers. Now, even integers, remember, can only even numbers are only ever positive. So this cuts us down to numbers like 2, 4, 6, 8, and so on. For notation, right, we'll write x and then this, well, looks like the such that symbol only backwards a little bit, right? So circle with a line there. X, we read that is x is an element of, or x is a member of the set A. Right? If you have a set with no elements at all, we call that the empty set, and we write that like a zero that's been crossed out. Right? So that's the empty set, has no elements at all. That's an important set because there are times when we'll want to show that maybe that something doesn't exist. So one way to prove that is that the set of all the things like that is the empty set. Well, one important thing that we will see a lot of in the homework is containment, proving that one set is a subset of another. So B is a subset of A, which we would write as B, and then that's like an elongated half oval, half of it, right? Underlined. So it's meant to look kind of like less than or equal to, but instead of a sharp sideways V for less than, it's kind of like this long oval, right? And again, if you're used to the idea of what less than or equal to looks like, it's supposed to imply that B is somehow smaller than A. And what this means literally is every element of B is also an element of A. And we learned all this logic stuff for a reason. Let's rewrite it with logic symbols now. So B is a subset of A if and only if X contained in B implies X is contained in A. So writing out things with logic symbols like this may seem like, oh my gosh, what am I doing? Writing all this if and then and implies and such that. And yes, but we've spent a long time getting used to working with those and getting good at working with those. And the reason was we could use them now. So when we start writing proofs with sets, writing out exactly what we're doing with logic symbols, we're trying to prove that this implies that, makes it much easier because now we go, oh, then maybe I need a direct proof to do that. Or maybe I need a proof by cases or whatever we need in that particular problem. Here's a particular problem. Um, this is a fact, right? This is an obvious thing that takes, almost no effort to prove. So we're going to do this one just to get practice at proving it. So if we let A be the set of all integers, again, those are numbers like 0, 1, 2, 3, 4, but also counting negative 1, negative 2, negative 3, negative 4. And we let B be the even integers. So again, those are even integers. So numbers like 2, 4, 6, 8, and so forth have to be positive. Then obviously B is a subset of A. How do we prove that? Well, what I'm saying is if X is contained in B, then X is contained in A. So I'm going to use a simple direct proof to do this. I'm going to assume that X is contained in B. Okay? That means that X is an even integer. That's what we know about that. Remember, when we do a direct proof of P implies Q, we assume the P and we start trying to figure out what that tells us, right? So if we assume that X is contained in B, that tells us X is an even integer. Well, that means X is an integer. So obviously X is contained in the set of all integers. So there we go. That was as obvious as it seemed. But thinking through this and realizing that, oh, I recognize all that logic stuff that we've suffered through. That's really important because when we do something much harder, it's that logic stuff that's going to bail us out and show us how to get out of this wilderness of things that we start writing down on our paper and trying to understand where to go next. Okay, what does equality of sets mean? Well, if A and B are sets, then A equals B, right? If B is contained in A and A is contained in B. Okay? So they each have to be contained in each other. Notice that this is going to set up lots of proof by cases for us. Because how do you prove that A equals B? Well, you have to prove B is a subset of A and A is a subset of B, which means that we're going to do this in two parts. First, prove that A is a subset of B, then prove that B is a subset of A. Proof by cases is just screaming out of here, right? If we write this with logic symbols, then I would say A equals B, if and only if B is a subset of A, and with our friend the wedge there for conjugation, okay? Conjunction, not conjugation, conjunction, and then A is a subset of B. Of course, what does that really mean? How do I show that something's a subset of something else? Well, what that really means is if X is contained in B, that implies X is contained in A. In that case, parentheses. And I have to show that X is contained in A implies that X is contained in B. So you see, this writing around in the logic symbols gives us our roadmap now for how to show something. If I need to prove that two sets are equal, then here we go. Right? I do it in two cases. I take an element of one set and show that it has to be in the other. I take an element of the other set and show it has to be in the first one, vice versa. Okay, proper containment. So one set is a proper subset of the other, right? Like we would say B is a proper subset of A. If A is contained in B, but B is not equal to A. And if you look at the symbol we use here, instead of looking like a less than or equal to, it's like a less than or equal to with equal to crossed out. Right? So sometimes people won't write the equal to crossed out. Sometimes they'll write just the half oval. But then that can be confusing because sometimes people use that to mean a subset. So I much prefer writing it this way when I'm trying to emphasize something as a proper subset. It's like less than or equal to, but I've crossed out the equal to part. Right? So what that means, written in symbols, B is a proper subset of A if and only if B is contained in A, and sorry, X is, let me try saying that again. X is contained in B implies that X is contained in A, and that it's a proper subset, meaning there exists a Y which is contained in A but not in B. Right? So think about what that says again. Where did this Y come from? Well, the first part of the and is that everything in X is also everything in B is also in A. The second part of the second parentheses there says there is something in A which is not in B. Okay, a little bit of notation here because we'll use this a lot throughout the rest of the class. We've talked about integers and positive integers and real numbers and so forth. There's standard mathematician notation for all these things. So in with the little black that font is called blackboard bold, where you make the letter with double lines in places. Um, that kind of an in is what we'll usually use for the set of all positive integers 1, 2, 3, 4, and so on. The integers themselves we use with the blackboard bold z. Now you may ask yourself, why z for integers, right? Why not I for integers? I mean, I get n, right? N's for number, right? So where did the z come from? Well, if you know any German, you might recognize where this comes from. The German word for number is Zahlen, and so that's where the z comes from. Um, Q, right, Blackboard bolded Q, is our notation for the set of rational numbers. So those, remember what a rational number is? Those are essentially fractions. But being more precise, it's the set of all m over n, where m and n are integers, and n equals 0. And since we're not doing an algebra class, I'm not going to talk about equivalence relations and how do you take care of the fact that a half and 2/4 are really the same number. I'm assuming that we know what that means when we write m over n, and we're not going to go into all that. Essentially, rational numbers, right? So why the q? Because they're quotients, one integer divided by another integer. As long as the denominator is not 0, then we're good. Blackboard bolded R stands for the set of all real numbers. So what's a real number? Well, that includes the rational numbers, but it also includes anything you can write with a decimal. That's maybe the best way to say it. So anything you can write out with a decimal. You do have to be careful because the number 0.99999 that keeps going forever is actually equal to 1. That's easy to prove, but we'll brush over that part and just think of real numbers as things we can write with decimals that go on, or not go on, right? Like 1/2 has a decimal that stops, right? But like pi has decimal expansions that go on forever. Um, Blackboard bolded C will stand for the set of complex numbers. So that's a real number plus a real number times I. Okay, so here's a theorem now. Z is a proper subset of Q. So the integers are a proper subset of the rational numbers. So there's two things we have to prove here, right? We have to prove that Z is a subset of Q and also prove the proper part, that there is something in Q which is not in Z. There is a rational number which is not an integer. Okay, so how do we do this? Well, simple direct proof. This is fairly trivial. Pick a number which is in Z. I'll call it M. Now, how do I show that it's a rational number, right? So, right, think about a number like 4, right? How do you write 4 as a fraction? Well, you'd write it as 4 over 1. So that's what we do here, right? So we take our number M, which is an element of Z, and then if we write that as m divided by 1, well, that fits the pattern for what it means to be a rational number because it's an integer divided by an integer and the denominator is not 0. So therefore, m divided by 1, which is also obviously equal to m, is an element of Q. So there we go. Z is a subset of Q. How do we get the proper part? Well, there is a lot of rational numbers. 3 halves is the one I picked to show on the screen, which is a rational number, but definitely not an integer. So Z is a proper subset of Q. So again, the important part of this is not so much, everybody knows without having to do much work that Z is a proper subset of Q, right? The important thing is think through the structure of the proof, because what I was doing was proving, you know, P and Q. So notice I had to do this by cases. I did one thing and then I did the other. Um, as you go through and look at all of these proofs, try to write out the P's and Q's and implies and the logical structure of what I'm doing, because when you get stuck and you don't know what's going on and you're totally bewildered by a proof, the logic is what will pull you out. Okay, here's another example. Let's let T be the set of all multiples of 3. Obviously, T standing for 3. So, in other words, it's a set of all n contained in Z. This is set builder notation. If you've forgotten how this works, the curly brackets mean I'm defining a set. This is the set of all numbers n, which are an element of Z, so all the integers n. That little vertical bar means such that, when I'm doing this in set builder notation, n is equal to 3k for some k, which is also an integer. So in other words, these are all of the multiples of 3. Now, if you see something like this for the first time, it's probably helpful to stop and go, wait, what? What would that mean? Well, if k were 0, you'd get 3 times 0. If k were 1, you'd get 3. If k were 2, you'd get 6. If k were 3, you'd get 9. If k were negative 3, you'd get negative 9. So we're talking about all the multiples of 3, both positive multiples and negative multiples, because I've written z there. So that includes positive numbers and negative numbers. Let's say S is the set of multiples of 6. So same thing, but just with a 6 instead of the 3. Then, of course, S is a proper subset of T. How do we know this? Well, straightforward direct proof again, right? Let's take an element of S, call it N, and then show that it's an element of T. Okay, well, if N is an element of S, that means it looks like 6K for some number K in the integers. Okay, now I've got to show that that N is also a multiple of 3. So how do I do that? Well, that's easy, right? You just factor the 3 out. So if N is equal to 6K, then I could rewrite that as 3 times 2K. And of course, 2K is an integer because K was, and multiplying it by 2 didn't change that fact. So N is now 3 times an integer. So that means that N has to be an element of T. And because N was an arbitrary element of S, every element of S is an element of T. Therefore, S is a subset of T. How do I get that it's a proper subset? Well, I just have to find something in T that's not in S, and that's easy enough. So here, like 9 is a multiple of 3, but not a multiple of 6, because it's 3 times 3, so you can't write it as 6 times something.